Hello everyone and welcome back to Math Made Easy. In our previous lecture, we introduced error analysis. We learned what an error is and why error occurs and how to measure errors using absolute, relative and percentage errors. We also discussed the two major sources of computational errors as well. Today, we will complete this chapter by discussing four important concepts. And the concepts will help us to understand how numerical computation behaves before we begin to study numerical methods. So, we'll start with the first concept, that is this accuracy. So, imagine you are participating in an archery competition and the center of the target represents the true value. And we know every arrow you shoot represents a measured or a computed value. So, if your arrow lands very close to the center, your result is said to be accurate. So, this accuracy becomes the degree of closeness of a measured or a computed value to the true or exact value. For example, if I take the true value as 100 and the approximation taken as to be 99.98, so this represents a very highly accurate value. Now comes the precision. Now imagine you shoot 5 arrows and all 5 arrows land very close together. But they may not hit the center, but they are still grouped closely. That is known as to be the precision. So precision becomes the degree of agreement among repeated measurements or computations. So I draw here 4 targets to represent different scenarios. So in the very first case, all the arrows are clustered very close to each other and they are also hitting the center of the target. So this means the measurements are very close to the true value, so they are accurate, and at the same time they are very close to one another, so they are also precise. And this is the best possible situation in science, engineering, or numerical competition, and hence represents the higher accuracy with higher precision. So, our numerical methods always should claim for both higher accuracy and higher precision. Now, look at the second target. This time, the arrows are spread out over different locations. They are not close to one another, so the measurements are not precise, obviously. However, notice that they are all distributed around the center. So, if we consider the overall result, the average of these measurements is still very close to the true value. Therefore, the measurements are accurate but they lack precision. And in practical terms, this means the experiment gives the correct answer on an average, but the individual observations vary significantly and hence represents the higher accuracy with lower precision. Now, this is one of the most interesting cases. Notice that all the arrows are grouped here very close together. And this tells us that every measurement is almost identical. So the measurements are highly precise. But there is a problem. The entire group is far away from the center of the target. That means every measurement is consistently giving the wrong value. Therefore, this case is higher precision but lower accuracy. This often happens when an instrument has a systematic error or has not been calibrated properly, and the results are hence consistent but inconsistently correct. So, represents the lower accuracy with higher precision. And finally, we have the worst possible case. Here, the arrows are scattered randomly and they are also far away from the center. The measurements are not close to each other, so they are not precise. They are also far from the true value, so they are not accurate. And such measurements are both unreliable and inconsistent. And in numerical analysis, we always try to avoid algorithms that produce results like this and represents the lower accuracy with lower precision. So, hence, we can conclude that this accuracy is all about the correctness and the precision is about the consistency. Now comes this significant digits. See, every computer stores only a limited number of digits, and every numerical method eventually round numbers. So, if we keep too few significant digits, the approximation becomes poor. And if we keep more significant digits, the approximation usually becomes more accurate. So, although computational cost also increases, therefore, choosing an appropriate number of significant digits is an important part of numerical computation. Significant digits are hence the digits that carry some meaningful information about the precision of a value. So, there will be some rules regarding finding the significant digits. So, here's the rule number one that says all non-zero digits are significant. That means if I write this 45875, there are five significant digits present here. Similarly, in the rule number two that says the zeros occurring between non-zero digits are significant. That means if I write 200506, that means all six digits are significant here. And another rule that says the leading zeros are not significant. If there are leading zeros, as in this example, if I write this 0.00254, that means only three significant digits are there. Now comes rule 4 that says if there are trailing zeros after the decimal points, they all are significant. That means if I write 3.4500, that contains five significant digits from here. And rule number 5 says the trailing zeros without the decimal places are ambiguous. That means if I write 2500 as because the scientific notations are preferred to be there. Now for the correct significant digits, that says an approximation is correct to one n significant digits if its first and significant digits agree with those of the exact value. So if I write the exact value as 3.14159,265, then the approximation becomes this 3.1416. We can compare it digit by digit. Now comes the propagation of errors. Error rarely remain isolated. Once an error enters a calculation, it usually affects every subsequent computation. And this phenomena is known as the propagation of errors. The propagation of error, we can say, is the process by which error in the input values influence the final computed result. We have few of the cases here. That is, in the very first case, we have this addition rule. So let's just suppose you have a number that is z equals to x plus y, and let the errors in x and y be delta x and delta y. So the exact value becomes this x plus delta x and the y plus delta y. So the exact result become x plus delta x plus y plus delta y. So since we have z equals to x plus y, the error in z becomes this z delta z equals to delta x plus delta y. When we add two quantities, each quantity carries its own uncertainty. Since both uncertainties contribute to the final result, their absolute errors add. Now comes the second case, that is the subtraction. So if I suppose the z as x minus y, so the actual value becomes this x plus delta x minus y plus delta y. Therefore, this delta z, the error in z becomes the error in x minus error in y. So whenever we talk about the maximum possible error, we ignore usually the signs because we don't know whether the errors are positive or negative. Hence, this delta z is lesser than equals to mod of delta x plus mod of delta y. Therefore, we can write it as this delta z equals to delta x plus delta y. Now comes the another case that is multiplication. So if we have this z number as x into y, we can simply differentiate it and make it dz equals to y dx plus x dy. And if I divide it with the z equals to x into y, we can get this dz by z equals to dy by y plus dx by x. This means the relative error in product will be equals to relative error in first quantity plus the relative error in second quantity. Multiplication basically changes the scale of the answer. Therefore, instead of comparing the absolute differences, we compare fractional differences, or it can be referred to as to be the relative differences. And that's why these relative errors are actually added up. Now, case is for division. Again, we have supposed a number that is z equals to x by y. Again, by differentiating, we got this dz by z equals to dx by x minus dy by y. Again, for maximum possible error, we ignore the sign. Therefore, we get the value as dz by z equals to dx by x plus dy by y. And the last case, we have this powers. Suppose we have z equals to some x to the power n. We have n that is coming from a whole number, or it can be any real number. Taking logarithms both sides, we got this log z equals to n into log x. And when we differentiate it, we got this dz by z equals to n times dx by x. And hence, we get the value for this dz by z equals to n times dx by x. Now the question here is why we need the propagation, and why is this propagation important actually? So let's imagine building a bridge. See, every measurement contains a tiny error, and when thousands of calculations are performed, those tiny errors accumulated. And if engineers ignore that propagation of errors, the final design may become unsafe. So, therefore, we can say that understanding error propagation is essential in engineering and scientific computing. And with this, we conclude our discussion on accuracy, precision, significant digits, and propagation error. These concepts form the foundation for numerical analysis and will help us to evaluate the accuracy and reliability of every numerical method we study in the future. So, in our next lecture, we'll begin exploring the intermediate value theorem, the mathematical foundation for the numerical method, and see how it will lead naturally to the bisection method. So, if you found this lecture useful, continue with the next video in the playlist so you don't miss the flow of the course. Until then, keep learning, keep questioning, and remember every great solution begins with a clear concept. This is Math Made Easy. Thank you so much, and I'll see you in the next lecture.